No discussion of radicals would be complete without a very powerful analogy, a very powerful translation technique. Every radical is nothing more than an exponent in disguise. And to illustrate what I mean, we're going to look in this example at how to compute some very interesting powers. Specifically here we have 1/9 raised to the power 3/2. And we also have 32 raised to the power -4/5. And so the operative question here is that we know how to raise a number to a whole number exponent. If I had 9 to the 3rd power, that just means to multiply 9 by itself, 9 times 9 times 9, right? But what does it mean to raise something to a 1/2 power, or a 3/2 power, or a 4/5 power? What do we do when the exponent is a fraction, a rational number instead of an integer? So here's our strategy. What we can do is we can think of that fraction, which is upstairs in the exponent, as a multiplication and division problem. That 3/2, for example, that's in the exponent of the 1/9. Let's think about that as multiplication by 3 and division by 2. And then we're going to make the analogy of what to do with a power when multiplication and division are happening in its exponent. We can turn multiplication and division in an exponent into the operation which is one step higher on the arithmetic layer cake happening to the power itself, which is exponents and roots. So all of that is a long-winded way of saying the following. If I have multiplication or division happening in the exponent of an expression, that is equivalent to exponentiation or roots happening to the power itself. And what that's going to do for us in the land of fractional exponents is we're going to think of the numerators of these fractions as something we multiply by in the exponent. We're going to think of the denominators of these fractions as something we divide by in the exponent. And then using this analogy, if I have any multiplication in the exponents, in other words, if I have a numerator of a fraction, that's going to turn into a power, an exponentiation. And if I have a denominator, if I have division going on in my exponent, that's going to turn into a root. And that's why we're talking about it in this context. We've been thinking about radicals a lot, so that's why this comes up here. So what's the process? First thing we're going to do here is if there's any distribution that we need to do of the exponent across multiplication or division, then we'll do that first. So in our example in part A, we've got a fraction and really a division problem inside those parentheses. So we're going to distribute that exponent across that division first. Then if there are any negative exponents to worry about, we'll resolve the problem with the negative exponents just by trading multiplication for division or vice versa. And then comes the fun part. Any denominator that I have in a fractional exponent becomes instead the index of a root that I can take with that base. And any numerator that I have of a fractional exponent turns into a power, an exponentiation that I can compute. And the great thing about these is we can do those two steps in either order. We can either think about the powers first and then take roots, or what's probably more easy is think about the roots first and then take the power. So these two examples hopefully will illustrate what I mean by that. I want to raise 1/9 to the power 3/2. So the first thing I'm going to do is distribute the power of 3/2 across the division, 1 divided by 9, on the inside of the parentheses. So in other words, I'm really looking at 1 to the power 3/2 divided by 9 to the power 3/2. Okay, great. If there are any negative exponents, we would resolve that now, but there aren't. Our exponents are all positive here, so we don't have to do step 2. So now we can think about the denominators of these fractional exponents. Those denominators can turn into indices of roots instead, indices of radicals. In other words, since these denominators are 2's, I can rewrite these expressions as radicals with indexes of 2, specifically square roots. Then the numerators turn into powers on their bases. So the bases were 1 and 9 here. So I'm going to take the numerators, the 3/2 has a numerator of 3, and make those powers on the 1 and the 9. So in other words, 1 to the 3/2 is nothing more than the square root of 1 to the 3rd. 9 to the 3/2 is nothing more than the square root of 9 to the 3rd. And I could go forward and simplify this way. The problem with that is that I would need to compute 9 to the power 3, which is, what is that, 729. And then I would have to simplify the square root of 729, which would give me a few extra steps to do. So if it's convenient, and it usually is, we can instead think about taking the roots first and the powers second. And that turns out to be the quicker way to go here. That works just because multiplication is a commutative process. And so if I want to multiply by 3 and divide by 2, that's the same as dividing by 2 and multiplying by 3. So whichever order we do it in will still give us the right answer. So the easier way to do this is to think of it as the roots first. So I'm taking the square root of 9 and the square root of 1, and then taking those numbers and raising them to the power 3. So the square root of 1 raised to the 3rd is 1 cubed. The square root of 9 raised to the 3rd is 3 cubed. 3, after all, is the square root of 9. And so to simplify, we'll just simplify 3 to the power 3 and 1 to the power 3. 1 cubed is 1 times 1 times 1. 3 cubed is 3 times 3 times 3, which is 27. And there's our answer. So to compute 1/9 to the power 3/2, we first applied that 3/2 power to both the numerator and the denominator, and then, this is the important part, used the denominator of that fraction to suggest the index of a root that we can take. The denominators were 2, so we ended up taking square roots, and then taking the numerators of those fractions and taking that power of the root that we just found, which turns 1/9 to the power 3/2 into 1 over 27. Let's use that same process to look at part B, which asks us to find the value of 32 to the power -4/5. And the step we're going to end up practicing over and over again is that step where we take the fractional exponent and turn it into a combination of a root and a power. In this example, though, the first thing we need to do is resolve that negative exponent. Rather than having 32 to the -4/5 multiplied by 1 out in front, we're going to trade a negative exponent for positive by trading multiplication in front for division. So this is really 1 divided by 32 to the +4/5. In other words, it's a fraction, 1 over 32 to the power 4/5. And now, let's resolve that fractional exponent 4/5 by first using the denominator to suggest the index of a root. 32 to the 4/5 can be computed by first finding the 5th root of 32, and then using the numerator, 4, to suggest a power of that number. So the 5 in the denominator becomes an index on a root, the 5th root of 32, and then we're going to raise that answer to the power 4. Well, what is the 5th root of 32? This is one that's probably worth knowing because it's rather simple. It turns out to be 2. 2 times 2 times 2 times 2 times 2 is 32. So that simplifies to 1 over 2 to the power 4. And then 2 to the power 4, 2 times 2 times 2 times 2 is 16. So again, the most important step, the one to practice over and over again, is where you turn that fractional exponent into a combination of a root first, whose index was the denominator of your fraction, followed by an exponentiation, whose exponent was the numerator of your fraction.